Diolch am ymuno ni yng nghanadledd Cenedlaethol Seren 2018. Ewch yn bellach. Thank you for joining us in the Seren National Conference 2018, Above and Beyond. Dyma sesiwn. This is session Peirianneg a Ffiseg, Engineering and Physics.
Welcome to this Physics and Engineering Masterclass. My name is James Bishop, and I'm a PhD physics student at the University of Sheffield. Can I just get a show of hands, everyone who knows what a PhD is? Do you know who a PhD is? What a PhD is? Okay, most people in the room. So just to clarify, a PhD is a degree that you do after a first degree. So I went to the University of Sheffield in 2011, and I did a 4-year master's in physics, and I'm now 3 years into my PhD. And I like to think of a PhD as kind of like a science apprenticeship, so you're doing research for your supervisor. So I'm just going to quickly go over the session and what we're going to be covering, if the slides will move. So first I'm going to give a brief overview of engineering and physics, which I think is actually, to be honest, impossible because it's such a broad field. But I'll try and summarize some areas that are interesting to me, at least, and what we do at the University of Sheffield. Then I'm going to talk about how we actually go about doing research. And in particular, I'm going to focus in on the scientific method. I'm sure you guys have probably heard of that before. A big chunk of this talk is going to be dedicated to me talking about my own research. So you might actually find at the end of this talk that you don't find my own research particularly interesting, but that's okay. There's a huge breadth of stuff you can do at university, not just what I do, basically. I'm going to finish the talk with some lessons for studying engineering and physics further, and that's going to be just some general tips that I think are helpful and that I wish I knew when I started my degree. And finally, I'm going to finish with a plenary where I'm going to give you some questions to answer based on what I've talked about in the talk, and you can ask me some questions if you want to. Throughout the talk, it's going to be mostly me lecturing. This is the kind of way you'll be learning at university mostly, although I will occasionally ask you guys to discuss stuff amongst yourselves and then feed back to me. Normally, people are quite shy at this point and they don't really want to talk to me. Yesterday, they were relatively talkative, so I'm hoping you guys will be as well. So, what is physics? Well, physics at its core is the exploration and understanding of the fundamental laws that govern the universe. And by understanding these laws, we can develop new technology that can improve everybody's lives. So physicists fall into two camps, theoreticians and experimentalists. Theoreticians propose and develop new mathematical models to predict how the universe behaves. So often the theoretician will be doing a lot of computational science, simulating a given system in order to predict or explain a phenomena. But theoreticians aren't really going anywhere without experimentalists. Now, an experimentalist is someone who tests these theories against observations of the real world using carefully designed experiments in order to ascertain whether the predictions are correct. As a whole, there are generally a lot more experimentalists out there than there are theoreticians, but physics particularly doesn't work without these two working together, essentially. So I'm just going to quickly summarize a few disciplines within physics and give you some examples of what the research is kind of looking at, trying to solve, the problems they're trying to solve. And I've only picked a few out here, and they're kind of the areas that we look at the University of Sheffield. So the first area is solid-state physics, which doesn't have the most exciting sounding name, to be frank. But this is the area that I work in, and it's actually a really important area where a lot of physicists and engineers work in. Solid-state physics is the study of solid materials with particular regards to their optical and electronic properties. So semiconductors are studied extensively in solid-state physics. One of the major breakthroughs in solid-state physics is the development of the transistor, which I'll talk a little bit about later. And this has led to stuff like a CPU, basically, the birth of computing. Without knowledge in solid-state physics, we simply wouldn't be able to live our lives the way we do today. So particle physics is another thing that we look at the University of Sheffield. And what I've put up on there is a chart of the standard model of particle physics. And what particle physics is trying to do is it's trying to summarize what the basic building blocks are of the universe, of matter, and the particles that interact with matter. Has anybody heard of a quark before? A lot of nodding going on, yeah. So the standard model is really cool, I think, because it basically summarizes all of the fundamental particles of the universe. So at the top left here, we have the quarks. We have up, down, charm, strange, top and bottom. Don't ask me why they're called this. They're really bizarre names. Bottom left, we've got the leptons. So you've probably heard of the electron, but then we've also got the mu and the tau. And then we've got various neutrinos that interact with those leptons. This column here is the gauge bosons. When we talk about physics, we generally talk about 4 fundamental forces of nature, Does anyone know what those four forces are? Can anyone give me an example of one? Yes?
Strong and weak nuclear forces.
That's two of them. Yeah. Okay, you've done all of them. You've saved the rest of the class having to do anything. Congratulations. So, the gluon is the gauge boson that's responsible for mediating the strong nuclear force. The photon is responsible for mediating the electromagnetic force. And the Z and W bosons, they're responsible for the weak nuclear force. The Higgs boson has only recently been discovered, and that's responsible for giving mass to all of these particles. Now, one boson that you might not see on there is the graviton. The graviton is a kind of theoretical particle which might mediate the gravitational force. But the thing is, we don't have a quantum explanation of gravity yet, and that's one of the big missing pieces in particle physics. It's one of the big unanswered questions. If we could find that, then we could explain basically all the forces of nature in one single theory. So another area we look at the University of Sheffield is astronomy. Astronomy is the study of celestial bodies such as stars, galaxies, black holes. I've got a little animation here that shows two neutron stars orbiting one another. And I don't know whether you guys are aware of this, but Einstein's theory of general relativity predicts that mass will distort space-time. And if you have two massive objects orbiting one another, they will generate waves in space-time. And up until very recently, it's been impossible to detect these waves. They've remained just theoretical. But only last year, a big collaboration, mostly in the US, but with some research at the University of Sheffield, was actually able to detect these gravitational waves for the first time. And that's exciting because it means we could have a whole new way of observing the universe rather than just using light. And the final area I just want to talk about is biophysics. This really cool animation shows a myostatin molecular motor. Now, this is within every cell in your body. The cell is basically held up by a skeleton of actin filaments. And along these actin filaments, we have these little molecules called molecular motors that just literally walk along the filaments, moving material around the cell. Biophysics is kind of an area that's becoming more and more prominent as biologists are kind of getting to the point now where they can't realistically explain how this thing functions without turning to physicists, essentially. So there's a lot of people at the University of Sheffield that work on this. And although this is an animation, you can actually look online and find some actual images of this using electron microscopy, I think. So I'm going to quickly talk about engineering, but as you probably already know, I'm a physicist. Engineering is the application of physical principles to design materials, structures, and technology. So some disciplines within engineering would be civil engineering, which is the design of structures such as roads, bridges, etc. Mechanical engineering, so anything that moves, engines, turbines, etc. Aerospace engineering, which is, as the name implies, aircraft, etc. And then finally, we have electrical engineering, so circuits and power transmission would kind of fall into that, I suppose. But one thing I kind of want to make clear is that the line is kind of blurred between physics and engineering a lot of the time. Even though I'm doing a physics PhD, I'd probably describe myself more as an engineer anyway, and I hope that will become clear as we kind of cover my own research in a bit. So earlier I was talking about solid-state physics. I just want to highlight how physics and engineering together can really help develop this new technology. Has anybody heard of a transistor before? A few nodding in the audience. What a transistor does is it basically allows you to switch off or amplify electrical current. And that might not sound particularly interesting, but when you miniaturize this onto a silicon chip, you can create a microprocessor that is the basis of actual computing. So you'll have one of these inside your smartphone or in your computer. And I don't know about you guys, but I really can't imagine living my life without a computer. And this technology wouldn't be around if it wasn't for the discovery of the transistor and the Nobel Prize it created in 1956. Another example of some solid-state physics technology is a laser. I've got one in my hand right now. Discovery of stimulated emission of light led to the development of lasers, which are now critical for telecommunications, amongst other applications. And that was a 1964 Nobel Prize. And some other examples here, we've got LEDs. That was the 2014 Nobel Prize for efficient blue LEDs. And then charge-coupled devices, and that was the 2009 Nobel Prize. So a CCD is basically a digital camera. Everyone's got one of these. I think they were initially developed for particle physics, but now they're very commonplace. So I kind of want to change gears a bit here and talk about the scientific method. I'd like you to discuss with your neighbour for a couple of minutes and just think about the scientific method and come up with some steps that you think might comprise it, and then afterwards I'll ask you guys to feed back to me. So go ahead. Okay, so does anybody have any steps that they might think make up the scientific method? An example of one would do. Any ideas? I remember. Oh, yep.
Is it when you come up with a theory, then you test it, and then find the theory?
That's a really good summary, actually, yeah. I guess the first step that I would say, if you wanted to break it down into a series of steps, is just to ask a question or to have a question that you want to answer. And you were kind of alluding to this when you were giving me your answer then. Have you heard of the term hypothesis? Yeah, so this hypothesis is basically this will be the theory that you come up with that tries to answer your question. The next step is going to be having a prediction that comes from your hypothesis. And this is kind of the difference, I think, between a scientific theory and this is what defines a scientific theory, basically, making this prediction that you can then test through an experiment. So obviously you perform your experiment and you'll see your results, and after you've done your experiment, you need to do some analysis of the data to actually decide what it's telling you. And then I think this is a step that's sometimes a little bit underplayed in science. I think it should be more important, is just replication, reproducing your experiment. It's all well and good to have one experiment that tells you something really interesting, but you have to go ahead and do it a few other times to check it's not an anomaly and to make sure it's a reliable result. The final step is probably one that you might not have talked about really, and I just kind of want to go into this talk, is publication. So you need to be able to share your work with other people working in the area. And this is kind of important if you want to actually work in science and get a career in science. So I want to kind of talk about my own research now. I don't know if you guys saw these news articles that came out at the start of October. This is from the IPCC, Intercontinental Panel on Climate Change, which is a UN body that looks at climate change. They published a report that said we're basically all screwed. And if we don't do something really drastic in the near future, we're going to be facing some serious problems, droughts, extreme weather, flooding, etc., sea level rises. I'm sure I don't have to explain to you guys what climate change is or what global warming is. I imagine you all know what that is. You're all bright, and I think you will cover it at primary school or secondary school. So I want to ask again a question. How do we combat climate change? Has anybody got any ideas? What could we do? Somebody's nodding at the front. You got an idea?
I was going to say assassinate Trump.
Assassinate Donald Trump. I think it would help, but I'm not sure it would fix the whole problem. Not pulling out of the Paris Climate Accords, yeah, that would help. So I guess you could come up with eating less meat would be a good one. Carbon capture of carbon dioxide that already exists in the atmosphere would help a lot as well. The one I want to kind of focus in is move away from fossil fuels and instead get our energy from a renewable source. So an example of a renewable source would be hydroelectric energy, wind, tidal, but the one I mainly want to focus on is solar because that's where my research is. I work in solar energy. So what is solar energy? Well, solar energy is the development and design of a device called a photovoltaic or a solar cell that is able to absorb light and directly to convert it into electricity. So the reason why we find solar particularly attractive is that the sun delivers more energy to the Earth in an hour than we consume as humanity in an entire year. So that's an absolute enormous amount of energy out there that we just need to harvest. So we just need to develop new types of technology that can do that. So again, I want to ask you guys another question now, just to discuss it amongst yourselves. Imagine that you were going into a shop and you wanted to buy a solar cell or a solar panel. What were the desirable things you'd want for that solar panel? I'll give you another couple of minutes to talk about it. A kind of hush has descended on the room without me actually saying anything. So does anybody have any ideas? Anybody have any ideas for what they think would make a good solar cell? Yes?
Efficiency.
That's the main one, yes. Can you elaborate on what you mean by efficiency without reading the slide?
Energy output versus the size of the cell.
Yes, actually that's a decent explanation, actually. I think probably a more simple one would be to say what percentage of light energy is converted into electrical energy. Have you got any other desirable traits for our solar cell? Yes?
Cheap.
Bang on. That's the third bullet point, so I'm not going to bring it up yet. Another one?
Not reflective.
Not reflective, that's a really good one, yeah. So silicon solar cells will have an anti-reflection coating put on them to make sure that we're actually absorbing light, not shining it off. That's a good point. Any other ideas? Yes? Large surface area, great point. And that's going to become very important later on in the talk, actually. Yes?
Longevity.
Longevity, thank you. Stability or longevity, yes. Last a long time without breaking, essentially. We've already had cheap. The other ones you've brought up, non-reflectivity, large surface area, they're also important. But I think these are kind of the three important ones, I suppose. Other ones you might have thought about were lightweight, flexible, We can't make flexible solar panels at the moment, but or at least they're not available in the commercial market, but potentially that might be something we want to do in the future. Okay, so those are the kind of the 3 bullet points I think are the most important. I just want to kind of show you now, and it might be quite difficult to see on this screen because it's quite small. This is a really important chart in solar energy. It's the National Renewable Energy Laboratory's best research cell efficiency table. So on the x-axis here we've got year, and on the y-axis we've got efficiency. So the year starts in 1975 and goes up to the present day. And this shows all the different technologies that exist to act as photovoltaic light absorbers. And it shows how their efficiency is improving as research continues, essentially. So I just don't want you to look at all of these. I'm just giving you an idea of how many there are out there. But these blue squares, I kind of want you to have a look at those, I suppose. That's silicon. If you look at in front of the desk, there's a silicon device there. I'm sure you kind of recognize them because you see them a lot on people's roofs and in solar farms. That's the most common technology that exists at the moment. It's already been commercialized. You can buy it in a shop or you can put it on your roof. And you can see that was kind of discovered or developed in the 70s. And it was about 12% efficient then, and now it's up to about 25% efficient. And now I kind of want to zone in on these dots here. These are yellow filled circles at the bottom right. These are a new technology that's just been developed, perovskite solar cells, and that's where I work in. So perovskites emerged in about 2012, and they were about 10%, and they've shot up in the last 3 years to be about 20%. So they're about as efficient as silicon, or they're getting very close. Some of you might be thinking this 20% efficiency doesn't sound that great, but there's actually a fundamental limit on how efficient a solar cell can be, and that's 33% efficiency. So anywhere in the 20s is actually pretty good. So yeah, there's a lot of other steps that need to go through, but this is the most important step, and it's called the Shortowski process for those who are interested. Not only important for solar cells, also very important for the development of transistors and CPUs. So the same material is used in your computer. So currently, silicon-based solar cells are by far the most common as they are both efficient, stable, and cheap. So 20% efficiency, 25-year plus stability, and they're less than $1 a watt now. And to put that in context, about 30 years ago, silicon was about $300 per watt. Now it's about 13 cents. So that's a dramatic reduction in price. However, they have one weakness, really, one main weakness, and that's that it takes a lot of energy to grow the pure silicon crystals, as you've already seen in that video. You have to go all the way up to 2,700 degrees. We have this concept in solar energy known as the energy payback time. So if you imagine it takes X amount of energy to actually make the device, you have to wait for your device on your roof or in your solar farm to develop that much energy or convert that much energy before you actually start making a profit, if that makes sense. So we want that energy payback time to be as short as possible. So for silicon, it's about 2 years. So here's the question. What if we could make solar cells as efficient as silicon, but at even lower cost, and without the need for high temperatures, so we could have an even shorter energy payback time? So that's where perovskites come in. So perovskites are an exciting new material that could potentially fulfill this ambition. Now, what is a perovskite? A perovskite is basically any material that has a specific ABX3 crystal structure. And there's a picture of this structure on the screen right now, and I've got a little 3D printed model on the desk. So after the talk, if you want to have a look at it, then you're welcome to. Basically, you have 3 different atoms or ions. You have the A ion, which sits in the middle, and then around the edge, you've got the B ion, which is surrounded by kind of like an octahedral cage of the X ion. These materials have been known for a while, but we've discovered in recent years that some perovskites are excellent semiconductor materials for solar cells, particularly lead halide perovskites. Now, what makes them really, really exciting is that they can be processed from solution. Now, what I mean by that is that you can basically dissolve the components of this structure in a solvent and then coat it very cheaply and quickly onto a surface. So I want to you can imagine basically like a printing press that would make newspapers. Imagine instead of doing this very slow process where you're growing this big silicon crystal, you're just very, very quickly printing the material. And you've got sheets and sheets and sheets of solar cells coming out very quickly at low cost. That's kind of the dream of this process. And there's a picture kind of what that might look like. It's called roll-to-roll processing. You'd be developing onto flexible substrates as well, which also gives you an advantage in terms of weight and cost. So I kind of want to give you some physics now rather than just me talking about physics. I want to explain how we make the solar cells and how we test them. So in my labs, this is what I do. I make solar cells and I test them. We start off with a glass substrate, which is coated with what we call a transparent conductive metal oxide. You don't need to worry too much about what that is. All it is a transparent layer that conducts electricity. And then what we're going to do is we're going to coat the solutions for the different layers of our perovskite device, one after the other basically. And we do this through a process called spin coating. And what that is you deposit your fluid onto the substrate and then you spin it really, really quickly. And what that does is it spreads the liquid out and it dries it and it creates your film. It works very, very well for small devices in the lab, but it's not good for an industrial process. And the reason for that is that 80% of the fluid you put on the substrate gets thrown off the sides. So that's too wasteful, basically. So we'll spin multiple layers on, starting with an electron extraction layer, and then we'll spin our perovskite light absorber layer on, and then we'll spin our electron injection layer, and then we'll finish off with a top electrode or cathode. And I've got a picture here of what one of these devices looks like, and I've brought some with me today as well. After the talk's finished, I'll give you a demonstration of this device in action. If anyone's particularly interested, we'll shine some light on it and we'll measure the current, basically. And that's how you test a solar cell. So you make contact to the top cathode and the conductive metal oxide to measure the current, and then you illuminate it with light. But we don't just illuminate it with any light, we illuminate it with light from a specific piece of equipment called a solar simulator. And this produces a very strong light source with a defined intensity with the same spectrum as the sun, so that all people working in solar energy can compare the efficiencies they're recording because they're all using the same light intensity. What actually happens in the cell physically is the light goes through the glass, in these transparent layers here, and it's absorbed by the perovskite. And what that does is the photons excite the electrons into higher energy states, so they're energetic, and all the cell does is it extracts these electrons and then they go around the circuit. And it's kind of like a pump, essentially. The electrons are pumped into higher energy states, they're extracted, they go back into the device, and then they're pumped back again by light. I hope that makes sense. If you want to talk a little bit more about the physics of solar energy, just ask me some questions at the end of the talk. So if perovskite solar cells are so good, why aren't they available to buy yet? Well, there are three big problems. Problem number one, stability. Perovskites are very, very unstable. They really don't like air, they don't like oxygen, they don't like water, and they don't even like ultraviolet light. There's a reaction with ultraviolet light and oxygen that will degrade the perovskite. So we need to figure out a way to stabilize these materials if we're going to actually make commercial products. The other problem is toxicity. So the best perovskites are lead halide perovskites, and I don't know if you know this or not, but lead is actually quite a poisonous material, so we need to be careful about potentially putting this technology out on the market. And the final problem kind of ties into what one of you guys said earlier. We need to make the devices bigger. I've already shown you that the devices we make in the labs are quite small. We need to show that we can make bigger ones as kind of a proof of concept for industry. And that's kind of the problem that my PhD is looking at. So my PhD goal is to demonstrate that we can use spray coating to fabricate efficient perovskite solar cells and use this technique to make larger devices. So I've got an image here from a paper where we've basically shown kind of a concept image of what we imagine this would look like. So we'd have a production line where we've got all the different layers of the device being sprayed one after the other. So now I'm just going to quickly show you guys a video that I took in our labs of me spraying one of these films down, just to give you an idea of what the process looks like, if it plays. So this is done inside a glove box. So as I've said, the perovskite's sensitive to oxygen and water. So when we process them in an environment where we've taken all the air out and replaced it with nitrogen, which is inert. So it's kind of hard to see, but there's a jet of this solution now which is coming out of this nozzle, and it's just kind of scanning automatically across the surface. So after we've coated this glass with our precursor, what we need to do now is just to dry the film, and then we just need to convert the precursor into the perovskite. So all we do is we put it on a hot plate, and this isn't at 2,700 degrees, it's only about 100 degrees Celsius. And you can see it's changing color now. What's happening there is that the solvent is being evaporated, and the heat is giving the perovskite material the energy to restructure itself into that specific structure that I showed you earlier. Now this is not sped up in any way, this is real time. So if you compare that to the speed at which they're making those silicon devices, this is a hell of a lot quicker. So now the material is black, it's absorbing light basically. So earlier in the talk I talked about the scientific method, and what I want to do now is put that into context or into action as to how we would do that in a research environment. So the first step in the scientific method that I mentioned earlier was a question. We need to have a question that we want to answer. And in my case, the question that I was trying to answer was, when I spray coat my perovskite films, I find that they are very rough and non-uniform. And that means they don't work particularly well. Is there a way that I can improve the uniformity of the films I'm producing? So I've got an image here on the slide that shows one of these spray-coated films that I was making a few months ago. And as you can see, it's got a few pinholes in the film, which isn't great. We want it to be nice and uniform. But I don't know if you can notice this, it's quite grey. And that means that it's particularly rough, so it's scattering a lot of the light, basically. That's what's giving it that characteristic grey colour. If I turn that film into a device and then I measure the current, I get this particular shape, which confirms that it is a solar cell, but it's only operating at about 10% efficiency, which isn't really good enough. I want to be higher than that. So the next step is a hypothesis. So other research groups working in this area have found that if you use a vacuum, you can actually improve the quality of the film. So what a vacuum is basically an environment where you've removed most of the air and the pressure is very, very low. So space, for example, is an example of a very high vacuum. So this is a picture from a paper, basically. So I had some colleagues in my group that basically said, James, why don't you try doing this step and see if it helps you out? So I made a prediction. What I'm going to do is I'm going to spray my film. That's going to be step one. And then before I put it on the hot plate, I'm going to whack it in a chamber, take all of the air out of the chamber, leave it at a relatively low pressure for a few minutes, and then I'm going to take it out and I'm going to heat it up. And then I'm going to see what's going to happen then. So the next step is experiment. I went and did this experiment. And you can see on the right here is a picture of one of these films after I've undergone this vacuum treatment step. And you can see again, I've got a few defects here, but I hope you can see that the film overall is a lot blacker than it was before. And in this bottom right image, which is probably kind of hard to see at the back, I've taken the film and I've caught the light with it. And you can see that it's reflecting quite a lot of the light. It's quite shiny. And in fact, the roughness of this film is around 20 nanometers roughness. And to put that in comparison, the previous films were about 100 nanometers rough. So this is a dramatic improvement in the quality of the film. If I turn that into a device and measure the current again, I get a power conversion efficiency of around about 18%. So that's a real improvement in the efficiency. So the next step is to do some analysis. So when I was talking about how we make the device, it's kind of like a sandwich. You just have multiple layers. And like a sandwich, if you cut it in half and look at it side on, you can see what those layers look like. The thing is, though, the actual thickness of the perovskite device is less than the width of a human hair. So around about a micron or two. So we can't image it using a traditional microscope. So we need to use an electron microscope, basically. So an electron microscope uses electrons rather than photons to do the actual imaging for you. So on the right here, I've got a SEM image of a vacuum process film. And you can see here, this is the glass here. This is the conductive oxide. This grey layer in the middle is the most important one. That's the perovskite. You've got your electron injection layer, and on top you've got your gold cathode. I hope it's easy to see that it's relatively flat, and you can just about make out the individual grains, potentially, that make up this polycrystalline film. On the left here is the film that hasn't been exposed to a vacuum, and you can see that the thickness is changing quite a lot, even on a relatively short length scale. So I hope it's kind of intuitive for you guys to understand that this is an improvement from that. So it kind of explains why we're getting better performance. So the next step in the scientific method is replication. So I need to just check that this isn't just a fluke. Like, for example, whatever reason this day it worked, maybe it won't work again. I went ahead and did that, basically. And normally we work on extremely small areas, about 4 millimeters squared. I went and increased the area to about 25 millimeters squared, which is still tiny, but it's slightly less tiny. But I hope you can kind of understand that research is kind of a process, a slow process often. You can't really make massive leaps forward. Sometimes you've got to you make those incremental gains. So the final step in the method is publication. So after I got all these results, I was like, okay, this is pretty good. I'd like to share this with the rest of the community, say this process works, and you can use it yourselves in your own labs. And you guys probably don't know much about scientific publishing, so I thought I'd just tell you a little bit about it now at the end of the talk. So basically, there exists a huge variety of different journals, scientific journals. Some of them you might have heard of. Has anybody heard of the journal Nature? Some nodding going on, yeah. So Nature is a very, very prestigious journal. If you get a paper in Nature, then it can make your career. Science is another big journal, or Cell for biology is an enormously high-impact journal. Well, the first thing you need to do, though, is decide where you're going to send your paper. And obviously, I was happy with this work, but I didn't think it was super, super groundbreaking, basically. So we went for the journal ACS Applied Materials and Interfaces. So the first step in the publication process is that you go to the editor. You send your paper to the editor, and he decides whether or not he thinks it's good enough for publication. And sometimes he says no, and he sends it back to you, and you have to go somewhere else. In this case, he said he liked the paper, but he then has to do a process called peer review. Now, peer review is really, really important in the scientific process. It's basically the quality control for the paper. So the editor will send the paper out to some anonymous experts in the field, basically, who then read it and decide whether it's scientifically valid or not. And more often than not, what they'll probably do is say, we like it, but we want you to make some changes. Sometimes they might reject it outright, but in this case, they said, we like it, can you just make some changes, though? And then we'll be happy to publish it, basically. So I went back and made these changes, and this process took about 4 months, and then about 2 weeks ago, we published this paper. One thing I kind of want to point out as well is there's a lot of authors on this paper, and that's I want to kind of drive home the idea that science isn't just something you do by yourself. It's a collaborative process. You're working with other people. It's a team effort. So future work for me anyway is just to try and make some basically bigger area devices. So I want to make a massive device, which is around about 10 by 10 centimeters, which is still tiny compared to a big silicon device. But as I'm kind of alluded to earlier, it's all about making those steps, incremental gains. Some other groups have actually already gone ahead and done this, so I'd like to do that myself. So as we're kind of getting close to wrapping up, I'm just going to give you guys some lessons for studying physics and engineering further, some tips that I think I would like to have known myself, I guess, when I was going in to do my degree. The first point on there is to take good notes. When you go to university, you're going to be learning in a very different style to what you're used to maybe at college or at school. You're going to be in lectures like this. There's going to be a person at the front of the room, and they're going to be talking at you for an hour or so. So you need to get into the habit of being able to take good notes. Kind of building on that is to read the textbook. At the start of any lecture course, the lecturer will say, here's the textbook for the course. You should probably go ahead and read it. And to be frank, quite a lot of students don't do that. A lot of times I didn't do that in my undergraduate. But the thing is, they often can explain things better than a lecturer can. I'm sure you've noticed this about A-level, is that the amount of material you're covering, you're doing it in a shorter amount of time than you would have done at GCSE, and it's going to be the same at university. The content's going to get harder, and the amount of time that you're going to have to learn it is going to get shorter. So reading the textbook actually can be really useful, because sometimes they explain things better than a lecturer can. And this is kind of like one that I think is quite important, actually. When you're faced with a difficult concept, try and break it down to the core principles behind it. I find myself doing this quite a lot now when I'm doing my own research. It's like I don't really understand what's happening, what I'm seeing. Just go back to some core principles, and sometimes they don't have to be that advanced. Something you might have learned at A-level might be enough to actually kind of dissect this problem that you're facing. And don't be afraid to ask for help. As I've already said, science is a collaborative endeavor, so you want to work with other people. And to be honest, if you've got a friend or a colleague, getting them to explain something they understand that you don't is actually beneficial for them as well. It's one of the best ways you have to learn. This last bullet point is kind of more relevant if you're going to do some experimental science, be it physics or engineering or whatever. And that's to try and be aware of your own bias when performing experiments and try and be realistic about the errors in your measurements. It's quite easy to get kind of sucked into your own work and think it's the best thing ever, or to try and cherry pick data to make it look as attractive as possible. And to be honest, even professional scientists get caught up in this as well. So just try and be honest with your own work. Another point I wish I'd put on here is somebody came and asked me a question in yesterday's talk saying, I like physics, but I'm scared of maths. And I said to him, yeah, I was as well. So I guess if you don't worry too much about the maths side of physics and engineering, you will be doing maths, but it's just a tool that we use. So if you have a passion for the subject, don't be put off by the fact that it's quite mathematical.